Previously, we looked at an application of second order nollies, holdies in the form of RLC series circuits, which is a very important topic in the study of electrical engineering. Now we're going to take a look at another application of those second order holdies, nollies in the form of mechanical engineering. And it's what's called the spring mass model. Sometimes it's called vibrations. But I'm going to describe the scenario and also, come up with the differential equation that describes this scenario. Right, so the title, spring mass, um, it has to do, so the spring is a spring that you might be able to envision, the spring that you'd find in a ballpoint pen, for instance. The mass is just referring to some object. And the way I'm going to set up the system, I'm going to set it up in a vertical way. So let's say we have, let's say this is our ceiling. What's going to happen is we're going to attach the spring to the ceiling and just let it hang. And then we're going to attach our object, our mass, to that spring. So let's go ahead and draw that, right? So once you do that, the spring will be extended somewhat, and it might oscillate a little bit. And yeah, so there we go. So let's say this is our system. And once it stops oscillating, the object is still attached, but it's at rest, then we're going to call this position equilibrium. So I'm just going to put a little dotted line right here. And this is what we refer to as equilibrium. And unless we apply some additional force to the system, it's going to stay in equilibrium. So what kind of forces could we apply? Well, we could then take this object and pull it down some more like that, right? And then maybe it'll be down here. And then once we release it, the system will always try to go back to equilibrium. So it's going to oscillate a little bit and hopefully, use up all this energy that we've given it, and it's going to come back to rest. Or we could push it up, maybe here, and again, release it, and again, it's going to oscillate, right? So we can disturb this system from equilibrium, and then once we do that, there's going to be some sort of oscillation. It's going to move, right? And our function of interest is how far from equilibrium is the object at any given point. So using these blue arrows, I'm going to call it displacement, because whether the object is below equilibrium, like down here, oh, let's get this off, or above equilibrium over here, we're going to call that displacement x of t. So x of t is defined as the displacement from equilibrium at time t, right? So at time t, x of t. All right, so what we would like to do is find a nice function, right? In fact, we would like to find an explicit function that only involves t that gives us this displacement. And then we would know where the object is at any given time. And once we know this displacement, which you could also think of you could think of the displacement as the signed, S-I-G-N-E-D, position. And once I know the position, I can find things like velocity and acceleration. So it's a really important function. All right, so let's think about what goes into this. Now, whenever you have a system where there's an object and that object can go, let's say, in just let's say it's two directions, right? It's either above or below. You would like to have some sense of orientation. So we are going to take down as positive, right? So that means whenever x of t is a positive number, it means the object is below equilibrium. And then we're going to take above, right, to be negative. So whenever x of t gives us a negative number, we're going to say that that object is above equilibrium. All right, so we've kind of set the framework. Now, once you build the system and then it starts, let's say it's put in motion, there are going to be several forces on this body. So what we're going to do is we're going to make a note of all these forces. They're going to be, they're going to be three internal forces and one potential external force. And then we're going to apply a nice conservation law that says, well, we can't create or destroy anything, therefore this must be true. All right, so I want to show you how it kind of develops. So the first force that I am going to look at is the force due to the object itself. So I'm just going to say the force, and I'm going to use M for the mass, right? So the force due to the mass. Well, from classical Newtonian physics, we know that force is equal to the mass of the object times its acceleration, right? Well, again, since x of t's are unknown function, we would like to write down all our forces in terms of this unknown function. That way we can put them all together and maybe come up with a nice equation. And we know that the second derivative of position is acceleration. So instead of writing F equals m times a, mass times acceleration, what I can write is mass times x double prime, or if I wanted to be fancy, I could use my double dot notation, right? So either way, right? So this is the force that's due to the mass. Now, in certain situations, depending on where the system is built, like where you actually build it, and once the motion begins, your object might be subject to a resistive force. In other words, friction, right? So if you build this in a vacuum versus if you build it just in a regular room, or if you build it underwater, right, there are going to be different resistive forces in all those mediums or those environments. So a second force is, I'll say F sub r. This is like the resistive force. This is due to the environment now, right? Now, there's a principle in engineering that says the force, the frictional force or the resistive force that's on a body in motion is proportional to its velocity. So in other words, the faster the object is moving, the greater the resistive force it will encounter, right? So and we've dealt with statements of proportionality before. So we know that if two things are proportional, then one has to be a scalar multiple of the other. So I'm going to use beta, and you'll see why. I'm not going to use a k, which we normally use. I'm going to use beta as my constant of proportionality. So let me say it again. The resistive force is proportional to the velocity of the object. Well, the velocity of the object is the first derivative of position. So I'll have x prime right there. Or if I want to do my dot notation, it'd be beta x dot, right? So right now we have a force that's due to the object, a force that's due to its surrounding medium, if you will, and there's also a force that is exerted by the spring itself, right? So for instance, when the object is above equilibrium, the spring is going to push it down because it wants to get it back to equilibrium. When the object is below equilibrium, the spring is going to pull it back up. So there's this push and pull, literal tension in this model. So the force that's due to the spring, and then there's a principle in physics. Now when you study springs in physics, you often encounter a law based on Hooke. So Hooke's law, and Hooke's law says that the force that's needed to either compress or stretch a spring a certain displacement, right, is proportional to the displacement, which kind of makes sense. the longer you want to stretch the spring, the greater the force you have to apply. And similarly, the more you want to compress the spring, the force or the greater, sorry, not the forcer, the greater the force you have to apply. So again, let's say it again. The force is proportional to the displacement. So it's another constant of proportionality, and the standard constant of proportionality that usually is used in Hooke's law is K, and it's proportional to the displacement. Well, we're using x to represent the displacement, so I'm just going to put my x right there, right? So we have these three forces. These are often referred to as internal forces, right? So these are often referred to as internal forces, again, because they're inherent to the system itself, right? Now, again, I just mentioned specifically like the resistive force. If you do this in a vacuum, then there might be no resistive force. So then your beta would be zero, right? But again, we have to account for a lot of these possibilities. Now, it turns out that there is the potential that you could have a system that's referred to as a driven system, like you drive it. So you're not just like either pulling it up or pushing it down and then leaving it to its own devices. You might actually apply what's called an external force, and that's often denoted F of t. So F of t is defined as an external force, right? Right, and this comes up when the system is what's called driven. So you have a driving force. Now, I mentioned that we're going to use a conservation law again, and there are lots of conservation law. It's basically saying that nothing can be created or destroyed, but we just convert it from one form to the next. And basically, the sum of these internal forces, right, must be equal to all the external forces that we apply, right? So let's write this down, right? So by our conservation law, we have this nice equation. So we have m x double prime plus beta x prime is equal to not equal, plus kx. So plus kx, and then that is equal to f of t, right? And this, believe it or not, is the famous spring mass model. And then, now I didn't write down specifically what m, beta, and k are, so let me do that. So little f of t is our external force. We define x of t as our displacement. M is the mass of the object, right? It's mass. And now I'll just write this little equation that is often useful. We know that weight and mass are related by our gravitational constant. So weight is m times g, and g is our, again, gravitational constant. So we might use this equation at some point. Beta is it's the constant of proportionality related to the resistive force. So we sometimes call it the coefficient of friction. So let's just use that phrase, the coefficient of friction, and that multiplies our instantaneous velocity. And then K is often referred to like it's our spring constant, right? Hooke's spring constant, right? So K is the spring constant, right? And typically your model is going to have at least the mx double prime term and the kx term, because you're going to have a mass and you're going to have a spring. You don't necessarily have to have a resistive force. Your coefficient of friction could be 0, and you don't have to have an external force. That could be 0. And if your external force is 0, then you have a nice holdie. If your external force is not 0, then you have a nullity. But we can handle all those cases, right? So I just wanted to take a few minutes to kind of derive this. I didn't really get deep into the physics and the engineering, but just kind of stating the principles that lead to this very important model. And what's interesting is when you compare this model to the RLC model that we looked at, you see how things align. Like the external voltage there is like your external force here. Your resistance in that model is like your coefficient of friction here. So when you look at all the components, you start to see the similarity. And whereas an electrical engineer would refer to it in a certain terms, then a mechanical engineer would refer to the model in different terms. A mathematician just sees the same thing. So again, math to me is like the great equalizer. You can have all these specialized models, but at the core, you have a mathematical model, and then we apply techniques to solve and understand what that model is saying. And which is why, again, if you want to understand the world around us, look no further than differential equations. So we'll stop here, and then in the next video, we'll do an example to illustrate this. But the nice thing is we have all the methods we need to solve these. We just needed to understand how it's set up and what the numbers represent. So see you in the next video.